Alright, in this video I'm working Calculus BC Homework 3.3, which is about absolute extrema, extreme value theorem, candidates test, closed interval test, whatever you want to call it. Okay, so the first question is determine if the function is guaranteed by the extreme value theorem to have an absolute maximum on the interval 0 to 5. Okay, guaranteed by the extreme value theorem to have an absolute maximum. That's obviously kind of some loaded language there. And we're going to say that is code for is continuous, because that's the condition we need in order to apply the extreme value theorem. Okay, so is continuous on the closed interval 0 to 5. Okay, so we're just checking to see, are there any discontinuities between 0 and 5? Okay, so for A, I'm going to do some investigation. 1 over 1 minus e to the x. Okay, well that could be discontinuous if 1 minus e to the x was equal to 0. And that would happen at x equals 0. Okay, so I've got a discontinuity on 0 to 5, so I would say no, this is not guaranteed by the extreme value theorem to have an absolute maximum on the interval 0 to 5. Okay, for B, 1 over x squared plus e, okay, we would be interested in, again, the denominator equaling 0. Okay, but if I say that, well, that's x squared equals negative e, which is a negative number. There's no solution to that, so I'm not finding any discontinuities in F. So I'm going to say yes, it's continuous, therefore guarantees an absolute maximum. All right, cotangent of x. Okay, well, maybe we should just rewrite that. So we think about cosine over sine. Sine is the displacement from the x-axis, so sine of 0 is 0. Okay, so 0 is in the interval 0 to 5. Also, pi is in the interval 0 to 5. Okay, that's a place where sine x equals 0 because sine of pi equals 0. And so I'm going to say no, it's discontinuous on that interval, so not guaranteed. All right, 1 over 1 plus cosine x. Okay, so thinking about the denominator, when would 1 plus cosine x equals 0? That would be when cosine x equaled negative 1. Okay, that'd be over here at pi. Okay, so x equals pi. That is in the interval 0 to 5. That's a discontinuity, so I'm going to say no, this function is not guaranteed to have an absolute maximum. E has a discontinuity. We know that's a jump discontinuity at x equals e. E is between 2 and 3, so I'm going to say has a jump at x equals e. Okay, so that's going to be no because the function is discontinuous. No, I think that function actually does have an absolute maximum on the interval. I think the maximum is going to be 1, but that's just, a coincidence, and it's not guaranteed by the extreme value theorem. Okay, f of x equals arctangent x. Whew. Think about that one. Not sure how I would say that. No, I think this is one of those things, kind of like the limit of arctangent x as x approaches infinity. It's one of those things I think you just kind of gotta know. I hate to say that, but arctangent is a function whose graph, it looks a lot like cube root, but it does have horizontal asymptotes at negative pi over 2 and pi over 2. Okay, and this function is continuous everywhere, so I'm going to say it's definitely continuous on 0 to 5, so that would be a yes. The next one, G, is going to be, oh, this is factorable. Okay, because if I had x squared minus, just plug in 3 for e, that would be x squared minus 6x plus 9. Okay, and I also see that it's, looking like it wants to factor with x minus e. This is going to be x minus e times x minus e. that would be equal to x minus e, but with a hole at x equals e. So I'm just going to say it's a removable discontinuity. At x equals e, which is still between 0 and 5, so since it's not continuous on the entire closed interval, we cannot guarantee the absolute maximum. Okay, and then h is x over e to the x. So because e to the x is never equal to 0 for any real x, we're going to say, okay, the denominator never equals 0, and so the function is continuous everywhere, and then that would be guaranteed by the extreme value theorem to have an absolute maximum on the interval 0 to 5. All right, number 2 is asking us to find the absolute minimum value of f of x is 2x to the 3 minus 12x to the 2 minus 30x on the interval 0 to 6. Okay, so we're going to make our table. Okay, if we're asked to find an absolute extreme, we're going to do the candidates test. And so we are... And now might be a good time to look at what we are asked for. We are asked for the value of f, so my answer eventually is going to come from that column in the table. Okay, and so I'm going to start by plugging in x equals 0 and x equals 6. Okay, when x equals 0, f of 0 is pretty clearly going to equal 0. Okay, and then f of 6, maybe I'll do that off to the side. So 2 times 6 to the third. Now, I'm pretty sure that's 16, but I'm not totally committed to that, but I see what's happening here with the arithmetic. Sometimes you gotta be careful, or not careful, creative with the arithmetic, right? So 12 is 2 times 6, x squared. And then minus 30x. Okay, and so that'll be 2 times 3 powers of 6 minus 2 times 3 powers of 6. That's 0, minus 30 times 6 would be 180. So negative 180. Okay, I've checked the endpoints. Now I need to check the critical points. So I need to be very clear about what I'm doing here. I'm going to set f prime of x equals 0. Say f prime of x is 6x squared minus 24x minus 30. Okay, this is looking pretty factorable. Okay, yes, I think, okay, multiplying to negative 5, adding to negative 4. So that would be x equals 5 and x equals negative 1. And negative 1 is not in the interval 0 to 6, so the only other critical point I need to check is 5. Okay, so I'll go over here, and I have the luxury, I can make that a little smaller. And I can say, all right, I can test out f of 5, which will be 2 times 5 to the third minus 12 times 5 squared minus 30 times 5. Let me see, okay, well, 5 to the third is 125. 5 times 4 is 100, so times 12 would be 300. And 30 times 5 would be 150. Okay, so 100 minus 300 is negative 200. And so the minimum value of f on the closed interval 0 to 6 is negative 200. Now the next one, yeah, see, we've got something different. Find the value of x. So we're interested in the x value at which we're obtaining an absolute minimum on the interval pi to 2 pi. Okay, Now, I do think you might be able to just think about this one. In terms of the unit circle and figure it out, but I think I'm just going to go ahead and plug in. Just draw myself a nice good sized circle. All right, at pi, sine is 0, cosine is -1. At 2 pi, sine is 0 and cosine is +1. And then find where g prime of x equals 0. That would be where cosine x minus sine x equals 0 on the interval pi to 2 pi. So that's going to be down here. Okay? We're both negative, and then the pi over 4 is where kind of the same kind of coordinates. So then it's going to equal x equals 7 pi over 4. Right, and then sine x plus cosine x. Oh yeah, this is going to be pretty negative. So g of, that's not 7 pi over 4. Clearly not teaching pre-cal this year. 5 pi over 4. I probably ended up with the right answer. I just thought that was what that was called. Okay, that would be... both cosine and sine will be -√2 over 2. Okay, so if I add the two halves together, I will get -1 square root of 2, which is going to be more negative than -1. Okay, so I'm going to get x equals 5 pi over 4. And the next one is asking us to find the absolute maximum value of this function on the interval 1 to 10. It's the value of f. So I'm going to be looking for my answer from there. Right. 1 and 10 are numbers we need to be running through here. Alright, f of 1 is going to equal 1 plus -1 to the 2/3 power. Okay, you could think about squaring it and then taking the cube root, or you could think about taking the cube root and then squaring. Either way, that's going to be +1, so 1 plus 1, that's going to be 2. Then f of 10 would equal 1 plus 8 to the 2/3. Okay, cube root of 8 is 2. Square 2, that's 4. So 1 plus 4, 5. And then we need to also check the critical points. So that'll be f prime of x, which equals 0 plus 2/3 of x minus 2 to the -1/3. Okay, and maybe I should rewrite that. So if I write it like that, you can see, okay, if x equals 2, then the derivative doesn't exist, okay? We've got division by 0 on the derivative, making that a critical point of f. So I'm going to need to check the value of f of 2. One plus 2 minus 2 is 0 to the 2/3. Okay, so that was not the location of a maximum, it was the absolute minimum. Okay, which actually that kind of makes sense, thinking about what that graph might look like if you were to graph it. It would probably have definitely a minimum value at x equals 2. I see that. Okay, so the absolute maximum value of f, that's going to be 5. Value of x at which g, this looks kind of interesting, Wait a second. This is not very much room here. And I'm not sure if what I was supposed to do on that one. Maybe I was supposed to realize that 1 to 10. Yeah, I think I just probably didn't leave enough room on that one. But this one, I see something going on here. It's like, okay, wait a second. G prime of x. This is an exponential function, and these have kind of like a limited behavior type, is what I would say. There's not too many different behaviors we can see out of these guys. So G prime is going to be negative 5e to the negative x. Okay, yes, I see it. So negative 5 is always going to be a negative number. And e to the negative x is always greater than 0. Okay, so I've got a negative times a positive here. And so I'm going to say g of x is less than 0 for all x in the interval 0 to 8 because it's actually true everywhere. So okay, that means that g is decreasing the entire time. On the interval 0 to 8, and therefore the value of x is at x equals 8. Okay, because it was decreasing the whole time, so it had its absolute minimum at the very end. All right, now over here, one of these, and these are, if you graph these ones with multiple absolute values in them, they have strange looking graphs. So here we've got g of x equaling this thing here, and we're asking what is the absolute maximum of g on the interval negative 3 to 3. Maybe there's something to be said for this, but I'm not seeing it, and I know these things can look all sorts of different ways, so I'm going to just use the candidates test, negative 3, 3, and we'll think about places where g is having a critical point. Yeah, g prime is not going to exist at x equals negative 3 from that thing right there, and then also at x equals 0 because of that. And you just know that because of the graph of y equals absolute value of x. That's kind of like the defining aspect of it is that it's sharp, so it wouldn't be surprising. You can graph it on Desmos and check if you want. So over here, g is going to equal 2 times 0 minus the absolute value of negative 15, absolute value of negative 15. All right, and then if I plug in 3, I'd get 2 times 6 minus 15. Okay, and I'll figure all that out later. And then 2 times 3 minus 5 times 0's absolute value. Okay, so this is negative 15. 12 minus 15 is negative 3, and this would be 6. So the absolute maximum value of g is going to be 6. Okay, now we're getting into some more interesting questions, and honestly, I had forgotten I put those on the homework. I'll say there's not a whole lot of optimization on any of my tests, any version, any of these like really kind of tricky problems. These are interesting to do for homework, definitely good practice, a must do the first time you go through the calculus course if you're going to go on to the second one because they're going to assume you've done it. All that stuff. So thinking about making this rectangle have maximum area. So the area is going to equal, okay, well, base times height. So base would be right minus left, x minus 4. And height would be top minus bottom. So the y-coordinate of the point on the graph is 1 over x squared. And the bottom is the x-axis, which is y equals 0. Okay, and I think, I'm just looking at this expression looks like it wants me to multiply it. So I'm going to have x minus 4 divided by x squared. I think I'm going to want to call that 1 over x minus 4 over x squared, though. And maybe I'll just, because I know I'm going to want to take a derivative, because that's, what we do around here, I'm going to rewrite it as negative power. Yeah, I like this. Okay, now if I want to make the maximum area, I should probably try to take the derivative and set it equal to 0 and maybe do a little bit more analysis. So I'm going to take the derivative, so that'll be negative x to the negative 2 plus 8x to the negative 3. Okay, and well, we can work with this. Negative 1 over x squared plus 8 over x cubed. Okay. Now, I think what we should do if we want to set this thing equal to 0, well, you could set it equal to 0. Yeah, that's what we should do. I was going to put it together with a common denominator, but I just don't really feel like doing that right now. So I'm going to set it equal to 0, and then I'm going to add that 1 plus x squared to both sides. So that would be 8 over x cubed equals 1 over x squared. I'm going to multiply both sides, or like cross multiply, so that would be 8x squared equals x cubed. Okay, I'm going to divide both sides by x squared, which is okay just as long as x isn't equal to 0. Now, I can see that because they actually told us in the problem x is greater than or equal to 4, I don't have to worry. I don't even have to worry about dividing both sides by x squared. It's not a big deal because x will never equal 0 in this problem. So it's going to be 8 equals x to the 3 divided by x squared equals x. Okay. Now what we should probably do is think about the area versus, area versus x. So the area when x is 8 is going to be 1 over 8 minus 4 over 16. Okay, I was using that formula right there. Okay, so that's 1/8 minus 1/4 is going to be, that doesn't make any sense. Oh, that's because 8 squared is not 16. That's where I went wrong. Okay, so 4 over 64 would be 1 over 16. 1/8 minus 1/16 is 1/16. Okay, that makes a little more sense. But I've done this whole problem wrong. Okay, that's not a very big rectangle, but if you think about when x is equal to, thinking about the endpoints. Okay, well, if x is equal to 4, there's no area on that rectangle. Okay. Area when x is 4, that's definitely equal to 0 because it's just, it's right there. Okay, no area. And as x approaches infinity, we can actually compute this limit. I didn't think about this, but we probably should. Okay, as x approaches infinity, I'm thinking about that underlined red equation. That's going to be approaching 0 minus 0. Okay, and that also makes sense because the rectangle is going to be getting really, really flat. Now, the base is going to be getting arbitrarily long, but, there's no height, so no area. All right, and so we're going to say, okay, definitely x equals 8. Okay, now here we've got some true-false statements. Assuming f is continuous on the closed interval 0 to 1. Okay, if x is 1/2 on the, or if x is 1/2 is the only critical point on 0 to 1, it's either the absolute maximum or the absolute minimum. It's the only critical point. I don't think that's true, because what if it was like x minus, I'm thinking about a cube root function, I mean not a cube root function, a third degree polynomial that looks like that, and maybe I didn't want, oh whoops, I didn't really want that to be an arrow. I want it to be a 0 and a 1. So that maybe that was happening at x equals 1/2. That's a critical point, but it's neither the absolute maximum nor the minimum. Okay, so I'm going to say that's false. If it's the only critical point and it's a local maximum, okay, it could be sharp or it could be, that's not looking good. Or it could be smooth. Okay, and it's a local maximum and it's the only critical point and the function's continuous. Yeah, I'm not going to be able to go, turn back and go any higher than that. This one is true. Okay, if x equals 1/3 is the only critical point on 0 to 1, and it's a local minimum. Okay, so I guess there's something significant about the fact that it's 1/3. And then I'll just say 1 is over here. It's a local minimum, then the absolute maximum is at x equals 1. No, not necessarily. I don't think that's... No, it could just be doing a lot of decreasing right at the beginning. So I think I'm going to draw this a little bit more like that. And, okay, I'm going to draw it really exaggerated. That is, the middle point is less than 1/3 of the way between the other two horizontally. I will draw this being the minimum. There we go. The absolute maximum was not at x equals 1. I would say for a lot of functions, it probably is happening at x equals 1. But then there could have been even... Oh, no, it said only critical point. I was going to say there could have been another turn back, but that was actually not possible. Okay. Now consider all lines in the... Oh, yeah, these problems, I thought they were very interesting. I saw a couple of these in AP Classroom. All right, so look at this question. It's talking about the line that goes from the origin through the point on the graph. And thinking about the value of x at which the line with the minimum slope occurs. I wonder, I feel like that's going to be when it's tangent. I just feel like that's what we're going to see. I'm not certain about that, but just looking at the diagram, it just like thinking about tilting that line, I feel like the minimum slope would happen when it was sitting all the way below the curve, kind of, and that would be when it was tangent. So I feel like that might be one way to approach this problem, and it might be actually why you end up seeing something's derivatives equal to 0. Okay, anyway, I'm just going to say this, the slope is what we're trying to take the minimum of, so maybe I'll call it m, and that's going to be y divided by x for that point xy, right there. Okay, but we've got a formula for y, so I'm going to plug in on that. X squared minus 4x plus 25 all divided by x. Okay, and I think again that would be worth it for us to do some algebra here. That would be x minus 4 plus 25x to the negative 1. Yeah, doubting that's still on the screen. There we go. Okay, so if I want to find the minimum slope, I'm going to take the derivative of m and set it equal to 0. So that's going to be 1 minus 0 minus 25x to the negative 2. And we're going to be interested in where that equals 0. So that's 1 minus 25 over x squared equaling 0. Okay, I think this one is an equation that is best solved with your eyes. That's going to be x equaling 5 or negative 5. And I think we're only interested in 1 to 10. Yeah, so x is going to be equal to 5. Now I think that's going to be my answer, but what I should maybe do is check the slope for x equals 5, and also check it at 1 and 10. And I'm pretty sure, like, I mean, the figure is not drawn to scale, but I still think it's going to be right. Okay, so the slope at x equals 5. So 25 plus 25 is 50, minus 20 would be 30 over 5 is 6. Then the slope at 1 would be 1 minus 4 is negative 3, plus 25 is 22 over 1. That is definitely a larger slope. Then when x is 10, I've got 100 minus 40 would be 60, 85 over 10. That's 8.5. Okay, yeah, definitely the minimum slope is happening at x equals 5. All right, here is a square root of 1 plus sine x. Asking, does the extreme value theorem guarantee c such that h of c less than or equal to h of x for all x on the closed interval pi to 2 pi? Okay, what this statement here means is that x equals c correspond, or is the location of absolute minimum. At least on the closed interval pi to 2 pi. Okay, and so the question is this function continuous? I think the only thing I could see that could go wrong with h would be we would take the square root of a negative number. But if you think about it, at the very least, the inside of the square root would be 0, because sine x can be as negative as negative 1. So, and I can take the square root of 0, that's 0. So I'm going to say yes. Explain because h is continuous. I'm going to say all x, because that's true. But it's definitely true on that interval pi to 2 pi. Then, does the mean value theorem guarantee a value of c such that h of c is the average rate of change of h over the interval pi to 2 pi? So this is the question, is it differentiable? Okay, so let's just go ahead and check to see if it's differentiable. I think we're going to do that by taking the derivative. Yeah, this is an interesting question. So 1 plus sine x to the 1/2 power. H prime of x, we're going to take the derivative of the outside, inside the same, and then multiply by the derivative of the inside. Okay, now I'm going to rewrite this, yeah, because I think, so that'll be a cosine x in the numerator. I think that'll make it easier for me to show you what's going on here. I'm going to have the 2 from the 1/2, a square root from the negative 1/2 power, 1 plus sine x. All right, so what's going to happen here is there's going to be times where the derivative is gonna, it's gonna be at pi and 2 pi. Well, I'm gonna really have to think about this. Okay, so if we think about the mean value theorem, it requires that the function be continuous on the closed interval, which it is, and differentiable on the open interval, pi to 2 pi, which in this case would not be a problem, right? Because pi and 2 pi are no, it's 3 pi over 2. That's right there in the middle. There's a point of not differentiability. Okay, I thought I'd set this problem up to have that happen. Okay, so sine of 3 pi over 2 is negative 1. Okay, so I'm going to say h prime of 3 pi over 2 does not exist because of division by 0. Okay, yeah. Cosine of 3 pi over 2 is... Ooh, 0 over 0. Yeah. So we've got a derivative non-existing there. And then I'm going to say, okay, well, as a result, no. Let me actually do some investigation, though. Okay, I should trust myself. That's just exactly what happened. You know, h of pi and h of 2 pi are equal, but there is no place where this derivative is equaling 0 on that interval. So that's actually pretty nice. I just made a graph of it on Desmos, and I could see that it was strictly decreasing, sharp corners strictly increasing, and there was no place where it was flat between pi and 2 pi. So, does the intermediate value theorem guarantee a value of c such that h of c is h of pi plus h of 2 pi divided by 2? Okay, now in this case, when they're equal, I don't think I realized that. This was just like kind of new terminology I had not been familiar with that I noticed recently. Okay, I guess I can work with that. I thought I'd show y'all this new terminology that I had not noticed before. Okay, h of pi plus h of 2 pi divided by 2, that's just the point halfway between, h of pi and h of 2 pi. That's just the average of them. So it's just right there in the middle. And so I've never seen them ask about the intermediate value theorem, but that's just asking, does h achieve the value halfway between where it started and where it ended? And that would be like, yes, because it's continuous. Okay, last couple we've got some particle motion. Okay, farthest to the right, farthest to the right. Okay, we're looking for the absolute maximum value of position. Okay, but this first one is only giving us velocity. Interesting. So this must just be some trig work. I don't exactly remember doing this, but I know I made this problem set. So, all right. So on the interval 0 to 2, that must have been 0 to 2 pi. Yeah, or 0 to pi. Hold on, let me think about that real quick. I don't know. Maybe I did intend for it to be the interval 0 to 2. Okay, so I'm going to draw a circle. And just think about t versus sine t. Okay, so t is going to start at t equals 0. And then it's going to increase, as we go around the circle in the usual way, until t equals 2, which will have me taking the sine of 4. Now, pi is 3.14. I think 4 is going to be like down here. Okay, so we go up, we go around, you know how it goes. And so what I'm going to say is like sine is thinking about the vertical displacement. Sine is going to be positive the whole time. The sine is positive, the sine is positive, up until there, and then sine is 0. And then it's going to be negative for a little bit. And this is velocity. So what I'm saying is velocity, I'm going to sketch the graph from t equals 0 to 2. Okay, well, it starts off 3 times 0, which is 0. And then it increases and then decreases in a way that we've kind of seen before. Okay. Not drawing to scale at all. And then it's going to go 3 times a negative number, which maybe I will switch up the color for. Let's say down here. Okay, well, it's gone negative. And, about like that. And that will be at the other end of the interval, the time interval. Okay. And so since the velocity was only positive and then only negative, okay, or t equals, what would that be? Whatever causes me to take the sine of pi. So that would be t equals pi over 2. And maybe I'll put that in right there. Okay, so when would be t equals pi divided by 2, and my reason would be is the only critical point I think I've explained my reasoning plenty well. Basically, the velocity was only positive, then it was only negative. It was the only critical point of position, and it was a local maximum, so it would be the absolute maximum of position. That would be a reason that would work. That's probably not the type of one I would ask you to explain your reasoning on a quiz or a test, because I'm not really trying to read all the stuff I would get back. So an object moves along the x-axis with velocity given by this other one, and here we're going to go from 0.5 to 1.5. I'm going to again be thinking about the circle. But however you need to do this, if you wanted to just kind of graph this using the window pane technique, you could totally do that. That would be a good use of graphing sine and cosine. Not something we do in this class all that often, so it's not something I just default to. Okay, so 1 minus 2 cosine of pi t. I'm going to do it, though. It's been a while for me. I'm not, like I said earlier, I'm not teaching pre-cal this year, so... Okay, 0.5 to 1.5. I'm just going to trust that that's kind of like one period. Alright, so cosine, it would normally start at the top, but it's negative cosine, so... Okay, hopefully I'm not needing to sketch more than one period here. Okay, I forgot the points in the middle. And the harder I tried, the worse it looked. That was really bad, though. I can do better than that. It's one more try. It's not good enough. Oh. There we go. All right, and so that would be, there's no phase shifts, so that would be t equals 0. The period would be 2. Oh, nice. 1, so that'll be 0.5 and 1.5, so we've got it graphed just like we need. Okay, and 1 minus 2 cosine, so it would go up to 3 and down to negative 1, putting the x-axis or the t-axis or whatever halfway in between. All right, there we go, and that is my graph. So, yeah, what we're supposed to see here is that on the interval 0.5 to 1.5, velocity is strictly positive. For the whole time, for all t in the interval 0.5 to 1.5. Okay, therefore, farthest right at the end of the time interval, right? Because it always had positive velocity, it was always moving to the right at t equals 1.5. All right, so that's all for this problem set. Thanks for watching.